Every compass on Earth quietly follows an invisible force. It has done so for centuries, guiding sailors across empty oceans, pilots through clouds with no horizon, and hikers along ridgelines where no trail is visible. Most people never think about why the needle moves the way it does. It simply works, the way electricity simply works, or the way gravity simply works. But this particular force is not fixed. It is not frozen in place the way most of us imagine it. It drifts, it bends, it weakens in some places and strengthens in others. And in the last few decades, it has started changing in ways that have caught the attention of scientists who spend their careers watching it closely. This is not a story about the end of anything. It is a story about a planet that is quietly, continuously alive beneath our feet, and about the small army of researchers around the world trying to understand what that life looks like from the inside. Far above the atmosphere, invisible magnetic lines stretch deep into space, quietly deflecting billions of charged particles racing outward from the sun every second. You cannot see this shield. You cannot touch it. And yet almost everything about the surface of this planet, including the fact that there is a surface with living things on it at all, depends on it holding its shape. Strip away the magnetic field for a long enough stretch of time, and the solar wind would begin stripping away the atmosphere along with it, the way it likely did to Mars billions of years ago. Earth is not protected by luck. It is protected by a process, one that is still running right now, deep inside the planet, and has been running for longer than there has been life to protect. To understand why researchers are watching the magnetic field so closely today, it helps to go back to where the story of geomagnetism actually begins, long before satellites, long before airplanes, long before anyone understood that the planet itself was a magnet. Ancient sailors noticed the strange behavior of lodestone centuries before anyone could explain it. A sliver of magnetized iron floated on a piece of wood in a bowl of water would slowly turn until it settled in the same direction every time. Chinese navigators were using early forms of the magnetic compass by around the 11th century, and the technology spread along trade routes into the Islamic world and then into Europe over the following centuries. For a long time, nobody knew why the needle pointed the way it did. Some believed it was drawn toward a magnetic mountain somewhere in the far north. Others assumed it pointed to a star. Centuries earlier, in China, the same magnetic mineral, lodestone, had already found an even earlier use that had nothing to do with navigation at all. The earliest known references describe lodestone spoons balanced on bronze plates as tools for divination and geomancy, part of the broader practice of feng shui, long before anyone thought to put a magnetized needle on a boat. It was only later, by around the 11th century, that Chinese texts describe sailors explicitly using a floating or suspended magnetized needle to find direction at sea, particularly valuable on cloudy nights and open water far from any landmark, a genuinely transformative technology that would eventually spread west along maritime and overland trade routes. The truth, that the entire planet behaved like a giant invisible magnet, would not be proposed clearly until 1600, when the English physician William Gilbert published a book called De Magnete, arguing from experiments with a spherical magnet he called a terrella, Latin for little earth, that the planet itself was the source of the compass's behavior. Gilbert carved his terrella from natural lodestone and used a small compass to trace how its magnetic behavior changed at different points across its surface, finding patterns that closely echoed what sailors had already reported experiencing on the much larger sphere of the actual Earth. It was one of the first purely scientific investigations of a natural phenomenon conducted in the modern sense, testing an idea through deliberate, repeatable experiment rather than accepting inherited explanation. And it helped mark a turning point in how Europeans approached questions about the natural world more broadly, several decades before figures like Galileo and Newton would become associated with the same experimental spirit. Long before Gilbert, though, there were already hints that something about the compass was shifting. 16th century navigators had noticed that the needle did not point at exactly the same angle in every port, and that the angle itself seemed to creep, year after year, in ways too slow to notice on a single voyage, but unmistakable across a lifetime at sea. One of the first attempts to actually chart this drifting behavior on a large scale came from the English astronomer Edmund Halley, better known today for the comet that carries his name. In 1701, Halley published a chart of magnetic declination across the Atlantic Ocean, based on data he collected during a series of naval voyages specifically undertaken to survey the field. It was among the first isogonic maps ever produced, and it captured, in ink and parchment, a truth that would take another century to fully explain. The invisible force guiding every compass at sea was not only different from place to place, it was changing everywhere, all the time, in a slow and steady creep, now known as secular variation. For the next 2 centuries, sailors and surveyors slowly mapped how the compass needle behaved differently depending on where you stood on the globe, a quantity called declination, the angle between the direction a compass points and true geographic north. Explorers noted that this angle changed not only from place to place, but from year to year, a discovery that unsettled anyone who had assumed the magnetic field was as fixed and eternal as the stars. It was not until the 19th century that this drifting, restless quality of the field was placed on a rigorous mathematical footing, largely through the work of the German mathematician and physicist Carl Friedrich Gauss. In the 1830s, Gauss developed a method using spherical harmonics to describe the shape of Earth's magnetic field mathematically, effectively separating the portion of the field generated inside the planet from the portion generated outside it in the upper atmosphere and beyond. His approach remains, in its essential mathematical structure, the same one used by modern geomagnetic models today. Gauss also helped establish an international network of magnetic observatories so that measurements from different countries could be compared using a shared standard. In a real sense, the systematic scientific study of Earth's magnetic field, the discipline now called geomagnetism, was born from that decade of careful, patient measurement. One of the most consequential discoveries in the entire history of geomagnetism did not come from studying the present-day field at all, but from reading a record of its ancient past, frozen into rock. In the middle of the 20th century, research vessels towing magnetometers across the ocean floor began noticing a strange striped pattern in the magnetism of the seafloor rock on either side of the mid-ocean ridges, alternating bands where the rock's magnetism pointed in the same direction as today's field, and bands where it pointed the opposite way. In 1963, the geologists Fred Vine and Drummond Matthews, building on an idea independently proposed by the Canadian geologist Lawrence Morley, realized that these stripes were essentially a tape recording. As molten rock rises up through the mid-ocean ridge and cools, magnetic minerals within it lock in permanently the orientation of Earth's field at that exact moment, like a compass needle frozen mid-swing. As the seafloor then spreads slowly outward in both directions from the ridge, it carries a matched, mirror image record of every reversal the field has undergone for millions of years, preserved in solid rock. This single insight did two enormous things at once. It provided some of the most convincing evidence yet for the theory of plate tectonics, confirming that the seafloor really was spreading apart the way a small number of researchers had begun to suspect. And it gave geomagnetism an entirely new archive to study, one written in stone rather than in observatory logbooks, stretching back tens of millions of years rather than a mere 2 centuries. A related technique called archaeomagnetism lets researchers push even further into the recent past using a very different kind of material, fired clay. When a kiln, hearth, or pottery vessel is heated to a high enough temperature and then cools, the magnetic minerals inside it also lock in a faithful record of the surrounding magnetic field at the moment it cooled. In much the same way as volcanic rock, by carefully dating archaeological artifacts and measuring the magnetism preserved within them, researchers have reconstructed detailed changes in the field's strength and direction across the last several thousand years of human history, filling in the gap between the geological record written in ocean floor rock and the direct instrumental measurements that only began in the 19th century. It is a strangely poetic partnership between two very different disciplines, archaeology and geophysics, meeting inside the same broken piece of ancient pottery. Declination was not the only quantity early researchers puzzled over. A compass needle, mounted so it can swing freely up and down, rather than only side to side, reveals a second property called inclination, or magnetic dip, the angle at which the field tilts into the ground. Near the equator, the field runs almost parallel to the surface, and a dip needle lies nearly flat. Near the poles, the field plunges nearly straight down, and the needle swings to stand almost vertical, pointing directly at the very spot geophysicists now define as the magnetic pole itself. Robert Norman, an English instrument maker, first described this dipping behavior in detail back in 1581, decades before Gilbert's book. And it was this simple, physical observation, a needle refusing to lie flat the further north you traveled, that first hinted the field was not simply pulling compasses sideways, but pouring, in 3 dimensions, into the planet itself, somewhere far to the north. By the time Gauss was developing his mathematical framework in the 1830s, he recognized that truly understanding the field required more than any single observer working alone. He helped establish what became known as the Göttingen Magnetic Union, an international network of researchers across Europe who agreed to take simultaneous magnetic measurements at fixed times, using standardized instruments and methods, so that observations recorded in different countries could be meaningfully compared and combined. It was, in miniature, the same basic principle underlying today's global network of geomagnetic observatories and the international collaborations behind missions like SWARM. No single station, no single country, and no single satellite can capture a field that spans the entire planet. Understanding it has always required people scattered across continents, agreeing to measure the same invisible thing at the same time and share what they found. It is worth pausing on how strange this discovery must have felt at the time. The ground beneath a person's feet, solid and unmoving, was somehow connected to an invisible structure that stretched out into the sky and shifted from year to year, obeying rules no one could yet explain. The answer to why it moved would not come from the surface at all. It would come from thousands of kilometers below it. To understand where Earth's magnetic field actually comes from, imagine peeling back the planet layer by layer, the way you might peel an onion, except each layer here is thousands of kilometers thick and exists under conditions almost impossible to picture. Beneath the crust we walk on, beneath the thick rocky mantle that makes up the bulk of the planet's volume, lies the outer core, a shell of liquid metal, mostly iron and nickel, roughly 2,900 kilometers beneath the surface. It is under immense pressure and at scorching temperatures, hot enough to melt iron completely, yet the churning inside is anything but calm. Convection currents, driven by heat escaping from the even hotter solid inner core beneath it, combined with the planet's own rotation, stir this liquid metal into slow, turbulent, swirling flows. Because the outer core is electrically conductive, this motion generates electric currents. Those currents, in turn, generate a magnetic field. Physicists call the whole self-sustaining system the geodynamo, and it is, in essence, exactly the same principle behind a bicycle dynamo. Motion of a conductor generating electricity, which generates magnetism, which then feeds back into the motion itself, sustaining the process for as long as the core keeps moving. This is not a simple, steady hum. The geodynamo is a chaotic system, meaning its behavior over long timescales is fundamentally difficult to predict, in much the same way weather is difficult to predict more than a week or two in advance, even though the physics governing it is well understood. Researchers can simulate simplified versions of the geodynamo on supercomputers, watching model oceans of liquid iron churn and twist across simulated millennia. But reproducing the exact, full complexity of the real core remains, for now, beyond reach. What scientists do know is that the magnetic field this process produces is not a clean, symmetrical bar magnet standing straight through the planet's middle. It is lumpy, uneven, and constantly reshaping itself, tilted at an angle to Earth's rotation axis, and marked by regions where it is unusually strong and regions where it is unusually weak. It is worth noting just how rare this kind of engine is among the rocky worlds of our own solar system. Mars, roughly half Earth's diameter, once had its own dynamo billions of years ago, evidence for which is still frozen into patches of magnetized crust across its southern highlands. But its core cooled and its dynamo shut down long ago, leaving the planet's atmosphere exposed and, over billions of years, largely stripped away by the solar wind. The Moon has never had a strong, sustained dynamo of its own. Venus, similar in size to Earth, appears to lack one today as well, for reasons still debated among planetary scientists. Earth, so far as researchers can tell, is the only rocky planet in the solar system where this deep internal engine has kept running continuously across the planet's entire multi-billion-year history. And that continuity is not a minor detail. It is very plausibly one of the reasons this planet still has an atmosphere to breathe at all. The consequences of that shield reach further than most people realize, extending into the behavior of living things themselves. A wide range of animals, including migratory birds, sea turtles, and even some species of fish and insects, appear to sense Earth's magnetic field directly and use it as a navigational cue, a sense researchers call magnetoreception. European robins have been shown in laboratory experiments to shift their migratory orientation when researchers artificially alter the local magnetic field around them. And sea turtle hatchlings, swimming out into open ocean for the first time in their lives, appear capable of using subtle regional variations in field strength and inclination to maintain a sense of position across thousands of kilometers of featureless water. The exact biological mechanism behind this sense remains an active and only partially resolved area of research, with competing hypotheses involving light-sensitive proteins in the eye and tiny magnetic mineral deposits in other tissues. But the existence of the sense itself is well documented across a surprising range of species. Long before humans built their first compass, it seems, the planet's other inhabitants had already found their own ways of reading the same invisible field. For most of human history, nobody could watch the geodynamo process directly because nobody could see 3,000 kilometers underground. What changed everything was the ability to watch the field's effects from above rather than trying to peer beneath the crust at all. And that shift did not happen all at once. It began quietly in the earliest years of the space age. The first satellites capable of measuring the magnetic field from orbit flew in the 1960s. But it was the Danish Ørsted satellite, launched in 1999, that marked the beginning of the modern era of high-precision magnetic mapping from space, followed by Germany's CHAMP satellite in 2000, which spent a decade gathering data before eventually burning up in the atmosphere in 2010. Together, these missions gave researchers their first sustained, continuous global view of how the field changes year to year. Data that fed directly into the International Geomagnetic Reference Field, a collaborative model updated roughly every 5 years by a worldwide community of geomagnetism researchers, and into the World Magnetic Model used for navigation. It was this steadily accumulating satellite record, stretching back across more than 2 decades now, that first allowed scientists to notice the North Magnetic Pole's dramatic acceleration in the 1990s for what it truly was. Not a measurement error, and not a local anomaly, but a genuine planet-scale shift in how the core beneath Siberia and Canada was behaving. Modern monitoring of Earth's magnetic field happens on almost every scale imaginable at once. Ground-based observatories, some of which have been recording continuous measurements for well over a century, track subtle daily and yearly fluctuations from fixed points scattered across the continents, often housed in unassuming buildings deliberately constructed without magnetic materials. No steel nails, no iron pipes, just wood and non-magnetic fittings, so that the instruments inside can detect changes as small as a fraction of a percent of the field's overall strength, without interference from their own walls. Some of these observatories, including stations in Europe with roots stretching back to the era of Gauss himself, have been quietly recording the field's daily rhythm for well over 150 years. An unbroken data set few other branches of Earth science can match. Research vessels tow magnetometers behind them across the open ocean, sometimes trailing the instrument on a long cable far enough behind the ship's own steel hull that the vessel's own magnetism does not contaminate the reading. Mapping magnetic stripes frozen into the seafloor that record the field's ancient reversals like a tape recorder running for hundreds of millions of years. Low-flying survey aircraft skim just above the ground in remote regions, sometimes only a few hundred meters up, following long parallel flight lines back and forth across a landscape for weeks at a time, mapping magnetic anomalies buried in the crust with a level of detail no satellite orbiting hundreds of kilometers overhead could ever achieve. And high above all of it, orbiting satellites now provide something no earlier generation of scientists ever had: a continuous, global, three-dimensional picture of the field as it changes in something close to real time. The centerpiece of that satellite effort today is the European Space Agency's SWARM mission, a constellation of 3 identical satellites launched in 2013, flying in carefully chosen orbits designed specifically to separate the different sources that contribute to the magnetic field measured at any given point. Untangling those sources is a genuinely difficult problem, because what a magnetometer in orbit detects is a combined signal, layered like sediment, blending the dominant field from the core with smaller contributions from magnetized rocks in the crust, electrical currents flowing through the oceans, and currents surging through the ionosphere and magnetosphere far above. By flying 2 of its satellites side by side at a lower altitude and one slightly higher and further apart, SWARM allows researchers to mathematically pull these different layers apart from one another, isolating the deep, core-generated signal that reveals what is actually happening inside the planet. It has become, in the years since its launch, one of the most important scientific instruments ever built for watching a planet's interior without drilling into it. There is one effect of this magnetic architecture that almost everyone has actually seen with their own eyes, even without knowing exactly why it looks the way it does: the aurora. Near the planet's magnetic poles, the same field lines that stretch out into space to deflect the solar wind also curve back down toward the surface, funneling charged particles from that wind down into the upper atmosphere along those lines, like water running down a drain pipe. When those particles collide with oxygen and nitrogen atoms high above the ground, they excite them, and the atoms release that energy as light: green and red for oxygen, blue and purple for nitrogen, rippling silently across the night sky as the aurora borealis in the north and the aurora australis in the south. This is why auroras appear overwhelmingly near the poles rather than the equator. The geometry of the field itself funnels the particles there. During intense geomagnetic storms, when the sun hurls an especially large cloud of charged particles toward Earth, that funnel widens, and auroras have on occasion been visible far outside their usual range, reported as far south as parts of the southern United States and southern Europe during particularly strong storms in the past 2 years, as the current solar cycle approached its peak activity. The Sun's own magnetic field runs through a roughly 11-year cycle of rising and falling activity, and the current cycle, the 25th since systematic numbering began in the mid-18th century, produced a run of unusually strong storms as it approached and passed its maximum, briefly turning the aurora from a rare, high-latitude spectacle into something millions of people far from the Arctic and Antarctic circles were able to step outside and see for themselves, often for the first time in their lives. Scientists at NOAA's Space Weather Prediction Center track these storms continuously, issuing forecasts in much the same way meteorologists forecast rain, because the same particles producing that beautiful display in the sky are the ones capable of inducing stray electrical currents in power grids and disrupting radio communication far below. Auroras have also, in recent years, become an unexpected meeting point between professional researchers and ordinary observers around the world. Citizen science projects invite members of the public to report aurora sightings, complete with location, timing, and photographs. Data that researchers then combine with satellite and ground-based instrument readings to build a far more detailed, real-time picture of how a geomagnetic storm is actually unfolding across the globe than professional instruments alone could provide. During the more active stretch of the current solar cycle, this kind of crowdsourced reporting has repeatedly helped confirm just how far from the poles a storm's effects had reached on a given night, turning what was once a private moment of wonder under a dark sky into a genuine contribution to ongoing scientific monitoring. Turning that scattered worldwide network of measurements, satellites, observatories, research vessels, survey aircraft, and now citizen aurora reports into a single coherent picture of the field requires a considerable amount of mathematics behind the scenes. Modern models, like the World Magnetic Model and the International Geomagnetic Reference Field, still rely at their core on the same basic mathematical approach Gauss pioneered nearly 2 centuries ago, describing the field using a set of spherical harmonic functions, essentially a way of building up a complex three-dimensional shape out of a series of simpler, smoother patterns layered on top of one another, each contributing a little more detail. In much the same way, a complex sound can be built up out of a combination of simple, pure tones. The specific weighting given to each of these patterns, known as Gauss coefficients, is recalculated every time a new model is released, using the latest satellite and observatory data fed through a process called data assimilation, a statistical technique for blending many imperfect, noisy measurements from different sources into the single best estimate of the field's true current state. It is, in a very real sense, still Gauss's method, run continuously, updated by satellites he could never have imagined, describing a field that has never once stopped moving since he first wrote the equations down. What SWARM and its predecessor missions, along with ground observatories and older records stretching back to the 1830s, have revealed, is a magnetic field in constant, uneven motion. Nowhere is that more visible than in the wandering of the North Magnetic Pole, a point distinct from the fixed geographic North Pole, where Earth's rotation axis meets the surface. The magnetic pole is defined instead by where the field lines dip straight down into the ground, and unlike the geographic pole, it has never stayed still. Since it was first located in northern Canada by the explorer James Clark Ross in 1831, it has traveled more than 2,200 kilometers. For most of that nearly 2-century journey, the pole crept along at a modest, unremarkable pace. Then, sometime around the 1990s, it began to sprint. Researchers watched its velocity climb from a slow crawl to as fast as 60 kilometers a year, a rate of movement so much faster than anything recorded before that the World Magnetic Model, the standard reference used by everything from smartphones to submarines, had to be updated a year ahead of its normal 5-year schedule in 2019 just to keep pace. But that wasn't the only surprise. Just as suddenly as it had accelerated, the pole's sprint began to slow again. According to the most recent geomagnetic models released by the National Centres for Environmental Information and the British Geological Survey, its speed has now dropped to roughly 35 kilometers a year, the largest single deceleration in pole speed researchers have measured. As of the latest release, the North Magnetic Pole sits at approximately 85.762 degrees north and 139.298 degrees east, a position that places it, for the first time in recorded history, closer to Siberia than to Canada. Why did it suddenly speed up? And why did it then slow back down? Geophysicists describe the likely explanation as a kind of tug-of-war happening deep inside the planet. Kieran Beggan, a geophysicist at the British Geological Survey, has explained that the overall strength of the magnetic field has been weakening beneath Canada while strengthening beneath Siberia, and that imbalance is effectively pulling the pole toward the stronger patch. Researchers using data from the SWARM mission have linked this to the movement of vast patches of magnetic flux at the boundary between the core and the mantle, essentially competing centers of magnetic influence whose relative strength shifts over years and decades dragging the surface expression of the pole along with them. But even scientists closely involved in tracking this movement are candid about the limits of current understanding. The exact reasons behind both the acceleration and the subsequent slowdown remain, in the words of researchers who study it, complicated and difficult to fully explain. Nobody can say with confidence whether the pole's pace will hold steady, slow further, or suddenly speed up again. The pole's dash toward Siberia is not the only place where the field has been quietly rewriting its own map. Just south of the equator, spanning the skies between South America and Southern Africa, sits a region known as the South Atlantic Anomaly, an area where the magnetic field is unusually weak compared to the rest of the planet. Its existence was already apparent in magnetic surveys taken in the 19th century, and by the early space age, it had become impossible to ignore, since the first satellites carrying particle detectors and onboard electronics kept registering strange, localized spikes in radiation and equipment errors every time they passed over this particular stretch of ocean, long before anyone had fully mapped why. Over the following decades, as the geographic center of the anomaly's weakest point was tracked more precisely, researchers documented its slow westward drift, from a position once centered closer to southern Africa toward one now centered nearer to South America, a shift that has unfolded over roughly a century. It is against that long backdrop that recent satellite data has revealed the anomaly behaving in ways that have drawn serious, focused scientific attention over the past 2 years in particular. A study published in the journal Physics of the Earth and Planetary Interiors, drawing on 11 years of measurements from the Swarm constellation, found that the anomaly expanded by an area nearly half the size of continental Europe between 2014 and 2025. Since around 2020, the weakening has accelerated even further in the section of the anomaly southwest of Africa, a pattern the lead researcher, Chris Finley, a professor of geomagnetism at the Technical University of Denmark, has linked to unusual magnetic structures at the boundary between the liquid outer core and the solid mantle above it. Structures known as reverse flux patches, where the local field points in the opposite direction from what the surrounding region would predict. Astronauts aboard the International Space Station have their own small visual encounter with the anomaly, even if most passengers on the ground never think about it. Cameras and sensitive electronics on board occasionally register brief streaks or glitches as the station passes through the region, artifacts of the same elevated particle radiation that concerns satellite engineers, a minor and well-understood nuisance rather than any danger to the crew, who remain shielded by the station's structure and by their own protective equipment during the short transit. It is worth pausing here on how this story tends to be told outside scientific journals, because headlines describing a growing weak spot in Earth's shield, sometimes dramatized further with language about a giant hole or a crack in the planet's defenses, can make a genuinely interesting, carefully studied phenomenon sound far more alarming than the underlying research actually supports. What the data shows is a real, measured, gradual change in a known feature of the field, one that satellite engineers have accounted for in mission planning for decades, and that shows no evidence, according to the researchers who study it most closely, of threatening anyone on the ground. Curiosity about what is happening deep inside the planet does not require exaggeration to be worthwhile. The unembellished facts, an ocean of liquid iron shifting its flow, a weak patch drifting and dividing above it, are remarkable enough on their own. Perhaps the most visually striking development is that the anomaly itself appears to be splitting. Earlier satellite observations from around 2015 to 2021 hinted that the single broad region of weak field was dividing into two separate low points, or lobes, one centered closer to South America and a newer one emerging to the southwest of Africa. More recent data appears to confirm that this division has continued, creating what NASA researchers who track the anomaly describe as two increasingly distinct minimum zones rather than one. Whether that trend continues, stabilizes, or reverses over the coming years remains an open and actively studied question. None of this is comfortable to imagine happening beneath your feet without wondering what it actually means for life on the surface. And that question deserves a careful, honest answer rather than a dramatic one. The South Atlantic Anomaly's practical significance today lies mainly in orbit, not on the ground. Its relevance is tied closely to a structure discovered only decades after the anomaly itself: the Van Allen radiation belts, donut-shaped zones of high-energy charged particles trapped by Earth's magnetic field. First identified by the American physicist James Van Allen using data from Explorer 1, the first satellite launched by the United States in 1958. Because the field is weaker over the South Atlantic Anomaly, the inner of these two belts dips unusually close to the surface as it passes over the region, in some places descending to within a few hundred kilometers of low Earth orbit, rather than remaining safely further out. Satellites and spacecraft flying through it are exposed to a noticeably higher dose of radiation than they would experience elsewhere in a similar orbit. Engineers have long known to design instruments and electronics with this exposure in mind, and mission planners routinely schedule sensitive operations, like certain spacewalks, to avoid the anomaly when possible. The International Space Station itself passes through the region regularly, and its onboard systems have occasionally experienced minor glitches attributed to the elevated radiation there, though nothing that has posed a serious danger to the astronauts aboard. On the ground, the anomaly creates no noticeable effects on daily life at all. Scientists studying it are careful to note that its expansion and splitting, while scientifically fascinating, fall well within the range of natural variation the field has displayed many times before, and current research has found no sign that it is a precursor to any larger, more dramatic event. The same caution applies to the broader question hovering behind almost every story about the magnetic field. Is this all leading toward a reversal? The dramatic event in which the north and south magnetic poles eventually swap places entirely? It is a fair question, because reversals are a real, well-documented part of Earth's history. The geological record, preserved in magnetized minerals frozen into rock as it cooled, both on land and on the seafloor, shows that the field has flipped polarity hundreds of times over the planet's history. The most recent full reversal, known as the Brunhes-Matuyama reversal, took place around 780,000 years ago, long before anything resembling a modern human existed to notice it happening. Reversals themselves are not instantaneous events. Based on evidence preserved in ancient volcanic rock sequences, researchers estimate that a full reversal unfolds over roughly 5 to 10,000 years, an almost imperceptibly slow transition on any human timescale. There is also a related but distinct phenomenon called a geomagnetic excursion, in which the field weakens dramatically and its poles wander erratically, sometimes even briefly tipping toward reversal, before recovering back to its original orientation without ever fully flipping. The most recent well-documented excursion, known as the Le Champ event, occurred around 41,000 years ago, and researchers studying sediment cores and ice cores from that period have been able to reconstruct its timeline in increasing detail in recent years. Over the past 3,000 years, paleomagnetic estimates suggest the overall strength of Earth's dipole field has been gradually declining, and some measurements indicate it has weakened by somewhere in the range of 9 to 30% over the past couple of centuries alone, depending on the specific data set and reference period used. Given all of that, it is entirely understandable that a growing weak spot, a fast-moving pole, and a long-term decline in field strength might sound, put together, like the ingredients of an unfolding reversal. This is exactly the point where scientific caution matters most. Researchers directly involved in monitoring the field, including those responsible for the most recent world magnetic model, have been explicit that current data show no sign of an impending reversal. The United States Geological Survey states plainly that while the global field is weakening and exhibiting anomalies, these trends remain within the range of natural, historically observed variation. Chris Finley, whose team documented the South Atlantic Anomaly's recent growth, has emphasized that the paleomagnetic record shows the field has weakened many times in the past without ever tipping into a full reversal, and that current changes are more likely to represent a fluctuation playing out over decades to centuries, rather than the opening act of a polarity flip. Scientists are careful to draw a firm line here between an observation, the field is weakening in specific regions and the pole is moving, and an interpretation. This means a reversal is imminent. The observations are solid. The dramatic interpretation is not currently supported by the evidence. That distinction between what is observed and what is merely speculated matters just as much when the conversation turns to the field's practical effects on modern technology. Because here, too, it is easy to overstate what a slowly shifting magnetic field actually means for everyday life. Aviation offers one of the clearest, least speculative examples of how magnetic changes ripple into daily operations. Runways around the world are named according to their magnetic compass heading, rounded to the nearest 10 degrees, which means that as the magnetic field shifts over years, some runways eventually require formal renumbering to stay accurate, a routine but genuinely necessary bit of housekeeping that aviation authorities have carried out for decades. Picture an airport crew repainting a runway number that has stayed the same for a generation, simply because the invisible line it was named after has quietly slid a few degrees since the last time anyone checked. Tampa International Airport in Florida offers a well-known real example. In 2011, its main runway was renumbered from 18R/36L to 19R/1L, a change of a single digit that represented years of accumulated magnetic drift, finally crossing the threshold that required an official update. A quiet bit of paperwork most passengers walking through the terminal that year never noticed at all. Aircraft still carry magnetic compasses as a backup navigation tool, even in the age of satellite positioning, precisely because backups need to work when primary systems fail. And an outdated magnetic model would quietly undermine that safety net without anyone noticing until it mattered. Nowhere does this matter more than on polar flight routes, where commercial airliners regularly cross close to the magnetic pole itself, on the shortest paths between cities in North America, Europe, and Asia. Near the pole, the horizontal component of the magnetic field weakens dramatically, since the field is pointing almost straight down into the ground, rather than along the surface, which makes ordinary magnetic compass readings unreliable, exactly where pilots might need a dependable backup most. This is part of why the high-resolution version of the World Magnetic Model, released for the first time in 2025, focused specifically on sharpening accuracy in these polar corridors, giving flight crews and navigation systems a far more detailed picture of a region where the old, coarser model left the largest margins for error. Submarines present a related but distinct case. Running silently beneath the waves, without access to GPS signals that cannot penetrate seawater, a submarine's navigation crew must rely on inertial systems combined with periodic corrections, and magnetic sensing remains part of that toolkit, making an accurate model of the field, updated to match its current drifting reality, a matter of real operational importance rather than mere convenience. In much the same way, satellite operators managing spacecraft that pass through the South Atlantic Anomaly build the anomaly's radiation profile directly into their mission planning, scheduling certain sensitive operations, including some spacewalks aboard the International Space Station, to avoid the highest radiation window if possible, treating this quiet region of weakened field not as a mystery to fear, but as a known, well-mapped hazard to plan around, the same way a hiker plans around a stretch of trail known for loose rock. This same protective shielding effect takes on a different significance once astronauts leave low Earth orbit entirely. Inside the magnetosphere, even within the weakened pocket of the South Atlantic Anomaly, the field still provides meaningful protection against the harshest radiation streaming from the Sun and from deep space. Venture beyond it, toward the Moon or on a future journey to Mars, and that protection largely disappears. This is precisely why radiation shielding is treated as such a central engineering challenge for crewed missions under NASA's Artemis program, and for any future crewed mission to Mars, a planet that, as already noted, lost its own protective dynamo billions of years ago. Engineers and mission planners study Earth's own magnetic environment partly because it offers the clearest working example of exactly what a spacecraft and the astronauts inside it will be missing once they leave its shelter behind. In that sense, the quiet, invisible field generated by the churning core beneath your feet is not only protecting the ground you stand on, it is also, indirectly, shaping how engineers design the spacecraft meant to carry humans somewhere that field cannot reach. GPS. Satellites themselves are not steered by Earth's magnetic field, since satellite positioning relies on precise timing signals rather than magnetic sensing. But many of the systems that translate a GPS position into a usable compass heading, the blue dot orienting itself correctly on a smartphone map, or a ship's electronic chart plotter, depend on geomagnetic models, like the World Magnetic Model, to convert between magnetic north and true north accurately. That is the quiet, invisible reason agencies like NOAA and the British Geological Survey update these models on a fixed schedule, and occasionally ahead of schedule when the pole is moving unusually fast, as happened in 2019. Submarines running silently beneath the waves, without access to GPS signals that cannot penetrate seawater, rely even more directly on accurate magnetic models for dead reckoning navigation, making precision here a matter of real operational importance rather than convenience. Power grids represent a different category of vulnerability, one connected less to the slow drift of the geomagnetic field itself and more to the space weather that field is constantly working to deflect. When the Sun ejects a burst of charged particles toward Earth in what is known as a coronal mass ejection, the resulting geomagnetic storm can induce electrical currents in long conductors on the ground, including power transmission lines, occasionally overwhelming transformers, and, in rare and extreme cases, causing regional blackouts. The most severe such event on record struck in September of 1859, an extraordinarily powerful geomagnetic storm now known as the Carrington event, named after the British astronomer Richard Carrington, who observed the solar flare that triggered it. At the time, the only long-distance electrical infrastructure on Earth was the telegraph network, and operators around the world reported sparks jumping from their equipment, some telegraph lines continuing to send messages even after being disconnected from their batteries, apparently powered by the induced current alone. A storm of that same magnitude, striking a modern world built on far more extensive and far more sensitive electrical infrastructure, is one of the scenarios space weather forecasters take most seriously today. A far smaller, though still significant storm, in March of 1989, induced currents strong enough to trip protective relays across the Hydro-Quebec power grid in Canada, plunging roughly 6 million people into darkness for about 9 hours. A widely studied case that remains a central reference point for engineers designing grid protections against future storms. A weaker or more irregular magnetic field in a given region does not cause space weather, but it can influence how efficiently that region's natural shielding deflects incoming particles, which is part of why researchers pay close attention to regions like the South Atlantic Anomaly when assessing radiation risk to infrastructure and to astronauts working in orbit above it. Communication systems, particularly high-frequency radio used for long-distance and polar aviation communication, also depend on a stable, well-modeled ionosphere, a layer of the upper atmosphere shaped in part by the magnetic field beneath it. During intense geomagnetic storms, disruptions to the ionosphere can degrade or temporarily black out these radio signals, an effect well documented and actively monitored by space weather forecasters at agencies including NOAA's Space Weather Prediction Center. None of these effects, taken individually or together, represent a hidden crisis unfolding beneath the public's notice. They represent the ordinary, continuous work of scientists and engineers, keeping increasingly precise models updated to match an increasingly well-observed, naturally dynamic system. Perhaps nowhere is that careful, ongoing work more visible than in the newest generation of geomagnetic models released in 2026. NOAA's National Centers for Environmental Information, working with the University of Colorado Boulder's Cooperative Institute for Research in Environmental Sciences, released an upgraded high-definition geomagnetic model this year, improving the resolution with which the field's crustal component can be mapped down to roughly 19 kilometers of detail, alongside real-time corrections for the disturbances caused by auroral currents in the polar regions, which can otherwise throw off sensitive directional drilling operations in places like Alaska and the North Sea. Alongside the standard World Magnetic Model for 2025, agencies also released, for the first time, a high-resolution companion version, sharpening the spatial detail of the model from roughly 3,300 kilometers at the equator down to approximately 300 kilometers, a jump intended to benefit polar aviation routes and other operations where fine-grained accuracy matters most. Where, then, does genuine scientific agreement end and open uncertainty begin? Researchers broadly agree on the fundamentals. The field is generated by convection and rotation acting on the liquid, electrically conductive outer core. The North Magnetic Pole is currently drifting toward Siberia, at a reduced but still historically elevated pace. The South Atlantic Anomaly has grown and appears to be splitting into two distinct lobes, and the overall dipole strength of the field has been gradually declining for at least the past few centuries, a trend visible in both historical measurements and paleomagnetic reconstructions. There is also broad agreement that none of these observations, individually or combined, currently indicates an imminent reversal. One of the most striking recent debates concerns a part of the planet even deeper than the liquid outer core, the solid inner core at Earth's very center. A metal sphere, roughly 70% the width of the Moon, floating within the churning liquid outer core and spinning largely independently of the rest of the planet. For decades, geophysicists have known that this inner core does not necessarily rotate in perfect lockstep with the mantle and crust above it, a puzzle scientists have worked to resolve using seismic waves from earthquakes, which change subtly in travel time depending on the exact orientation of the inner core they pass through. In 2024, a team led by John Vidal at the University of Southern California, analyzing waveform data going back decades, reported clear evidence that the inner core's rotation, relative to the surface, had been slowing since around 2010, appearing to pause and possibly even reverse direction relative to the mantle above it. The following year, the same team published a follow-up study in Nature Geoscience, suggesting something even stranger was happening at the same time. Seismic signals recorded at stations in Alaska and Canada showed differences that a change in rotation alone could not fully explain, leading the researchers to propose that the surface of the inner core itself might be physically deforming, its topography rising and falling in ways Vidal himself has described as difficult even to visualize. Some researchers who were not involved in that particular study have pushed back, suggesting that the observed seismic changes could reflect structural changes within the inner core, rather than deformation of its outer boundary, a disagreement that remains unresolved. Adding yet another layer to the puzzle, a separate research team reported evidence in late 2025 that iron deep in the inner core may exist in an unusual superionic state, a phase of matter distinct from solid, liquid, or gas, in which lighter elements move freely through a rigid iron lattice. A finding that, if confirmed, would reshape how researchers think about the core's physical properties altogether. None of this inner core behavior directly drives the surface magnetic field in a simple one-to-one way, since the field itself is generated primarily in the liquid outer core above it. But the debate is a vivid reminder of just how much remains genuinely unresolved about the planet's interior, even at a moment when satellite data has never been more detailed. A related and still only partly understood phenomenon, known among geomagnetism researchers as a geomagnetic jerk, adds another layer to the puzzle. Rather than changing smoothly and predictably from year to year, the rate at which the field's secular variation evolves occasionally shifts abruptly, almost like a sudden change of gear, over a period of just a year or two, before settling into a new, different trend. These jerks have been documented in the observatory record repeatedly since the middle of the 20th century, and researchers increasingly suspect they are linked to rapid pulses of motion in the liquid outer core, sudden accelerations in the flow of molten iron that momentarily outpace the slower, steadier convection driving the geodynamo's usual behavior. Some researchers have proposed that these jerks are connected to hydromagnetic waves, a kind of slow-moving wave of disturbance rippling through the electrically conductive fluid of the outer core, somewhat like a ripple crossing a pond. though the precise physical trigger for any individual jerk remains difficult to pin down after the fact, let alone predict in advance. The practical significance is that models like the World Magnetic Model, built in part by extrapolating recent trends forward in time, can be caught off guard when a jerk occurs partway through a 5-year forecast window. Part of why researchers continue debating whether more frequent updates or entirely different modeling approaches that account for the possibility of sudden jerks might serve navigation and industry better in the future. Where uncertainty remains regarding the surface field specifically is deeper and more fundamental. Scientists do not yet have a complete explanation for why the pole accelerated so sharply in the 1990s and then decelerated just as sharply in recent years. They do not fully understand why the South Atlantic Anomaly is weakening more intensely on its African side than its South American side, though the presence of an unusual geological structure deep in the mantle beneath Africa is suspected to play some role in shaping the pattern. That structure, known as the African Large Low Shear Velocity Province, is a vast, continent-sized region, roughly 1,800 miles beneath the surface, where seismic waves travel unusually slowly, suggesting rock with different density or composition than the surrounding mantle, quite possibly hotter or chemically distinct material that has sat largely undisturbed near the core mantle boundary for a very long time. Researchers suspect that this dense structure disrupts the smooth flow of the liquid iron directly beneath it in the outer core, weakening the local magnetic field generated there in a way that echoes upward all the way to the surface as part of the anomaly. It remains, however, a suspected contributing factor rather than a fully confirmed, settled explanation, and untangling exactly how a slow-moving structure in the solid mantle influences the much faster-moving liquid metal directly below it is an active area of geophysical modeling. And while supercomputer simulations of the geodynamo have grown remarkably sophisticated, reproducing many general features of the real field, none can yet forecast the specific behavior of the actual core with the kind of precision that would let researchers predict years in advance exactly how fast the pole will move or how the anomaly will evolve. Short-term forecasts, on the order of 5 to 10 years, have proven statistically reliable. Long-term predictions, stretching decades or centuries into the future, remain, by the admission of the scientists producing them, considerably more speculative. This is, in many ways, the honest state of an active scientific field. Substantial, hard-won knowledge sitting directly alongside genuine, acknowledged uncertainty, with researchers continuing to push the boundary between the two outward, one satellite pass and one supercomputer simulation at a time. That effort is not slowing down. The Swarm mission, now well past its original planned lifetime of roughly 4 years, and still returning data more than a decade after launch, continues gathering measurements, and its 3 satellites have already outlived several rounds of internal predictions about how long their instruments would keep functioning reliably in orbit. Space agencies have discussed follow-on missions designed to extend this kind of high-precision magnetic monitoring even further into the future, building on more than a decade of continuous measurement that has already transformed scientists' understanding of how the field's various components, core, crust, ocean, and ionosphere, interact and can be mathematically separated from one another. Any successor mission would need to match or improve on Swarm's unusual multi-satellite geometry, since it is precisely that careful arrangement, 2 satellites flying side by side at low altitude and one higher and further apart, that allows researchers to isolate the deep core signal from everything layered on top of it. Engineers involved in planning future geomagnetic missions have discussed pairing satellite data even more tightly with ground and airborne surveys than current missions already do, aiming for a genuinely seamless picture of the field from the core all the way out to the edge of the magnetosphere, rather than the somewhat separate strands of core, crustal, and external field research that different specialists have traditionally pursued on their own. Ground-based observatory networks continue expanding their coverage as well, particularly in regions of Africa and the Southern Hemisphere that have historically been underrepresented in global magnetic monitoring, compared to the dense observatory networks long established across Europe and North America. This is not a minor gap to close. Researchers studying the South Atlantic Anomaly have pointed out that the data from exactly these underrepresented regions has proven critical for understanding why the anomaly behaves so differently over Africa compared to South America. And international collaborations involving universities and geological surveys across multiple continents continue working to install new magnetometer stations in locations where coverage has historically been thin. Each new station added to this network, however modest it might seem on its own, a single instrument in a small, non-magnetic building in a remote corner of the world, adds one more thread to a global tapestry of measurement that has been slowly, patiently woven together since Gauss first proposed the idea of a coordinated international effort nearly 2 centuries ago. At the same time, modelers continue refining their supercomputer simulations of the geodynamo itself, incorporating ever more detailed physics of core convection, rotation, and the electromagnetic coupling between the core and the base of the mantle. These simulations have grown remarkably sophisticated over the past 2 decades, now capable of reproducing many general features of the real field, including its tendency to occasionally reverse polarity over geological timescales. But running a simulation detailed enough to capture the full turbulent complexity of the actual outer core remains, for now, at the edge of even the most powerful computing resources available to researchers. Closing that gap between a model that behaves somewhat like the real geodynamo and one that can be trusted to forecast its behavior decades into the future with real precision is one of the central long-term goals of the field. Open questions remain plentiful, and scientists studying the field seem, if anything, energized rather than troubled by them. What exactly triggers a sudden shift in the pole's velocity, and could it happen again with as little warning as it did in the 1990s? What is truly driving the divergent behavior between the African and South American sides of the South Atlantic Anomaly? And what role, if any, does the vast, unusual rock formation deep in the mantle beneath Africa actually play in shaping it? How closely connected are the deep, slow-moving structures at the boundary between the core and mantle to the surface changes researchers can actually observe from orbit? Is the debate over the inner core's shifting rotation and possible deformation a sign of something meaningfully connected to the surface field's behavior, or a largely separate story playing out at the very center of the planet? And on a longer timescale that stretches well beyond any single research career, what combination of conditions inside the core eventually tips a weakening, wandering field into a full reversal, rather than settling back down the way it has after every excursion recorded in the geological past? Answering any one of these questions fully would represent a genuine milestone in the Earth sciences, and researchers around the world, from satellite engineers in Germany and France to seismologists in California and geomagnetism specialists in Denmark, are actively working, piece by piece, toward that goal right now. There is something quietly remarkable in all of this. something easy to lose sight of amid discussions of anomalies and drifting poles and radiation belts. 3,000 kilometers beneath the ground you are standing on right now, an ocean of liquid metal is moving, slowly and immensely, driven by heat left over from the planet's formation more than 4 billion years ago. And that motion is, at this very moment, generating the field that keeps a livable atmosphere wrapped around this planet, deflecting a storm of charged particles that never stops arriving from the sun. It has been doing this, in one form or another, for essentially the entire history of complex life on Earth.
It has reversed itself hundreds of times, weakened and recovered dozens of times more. And through all of it, life continued, adapted, and in time, built compasses, and then satellites, and then constellations of satellites specifically designed to watch this process unfold from above. Think for a moment about the scale of patience this story actually represents. William Gilbert carved his little lodestone Torella more than 4 centuries ago, trying to understand a force he could measure but never see. Edmund Halley sailed across the Atlantic, charting a needle's whisper of deviation, one port at a time. Carl Friedrich Gauss sat with pen and paper, describing in mathematics a field no human eye would ever witness directly, work so enduring that satellites launched nearly 2 centuries later still rely on the shape of his equations. Each generation added a little more precision to the picture, a little more nuance, without ever fully closing the gap between what is known and what remains genuinely uncertain. That gap has not disappeared today. In some ways, it has simply moved from questions about where the pole sits on a map to questions about what stirs 3,000 kilometers below it. From whether a compass will point true to whether a weak spot over the South Atlantic will keep splitting apart. From whether the inner core is spinning normally to whether its very surface is quietly reshaping itself in the dark. None of this uncertainty is a sign of a science struggling to keep up. If anything, it is a sign of a science finally equipped to ask sharper questions than it ever could before. A century ago, nobody could have told you the North Magnetic Pole's exact coordinates to a fraction of a degree, let alone tracked its acceleration and deceleration decade by decade. Nobody could have mapped a weak patch in the field over the South Atlantic splitting into 2 lobes, because nobody had a constellation of satellites flying in careful formation specifically designed to isolate that signal from everything layered on top of it. Nobody could have detected the faint, subtle, seismic echo of the inner core possibly changing its rotation or its very shape 3,000 kilometers underground. The tools available to researchers today, swarms, magnetometers, decades of seismic recordings from earthquakes on the far side of the planet, supercomputer simulations of a churning ocean of liquid iron, satellite-fed models updated with real-time solar storm data, represent a genuinely new kind of vision into a process that spent nearly all of human history as pure invisible mystery. The magnetic field is not a fragile relic on the verge of failing. It is an ordinary, extraordinary feature of a living planet, doing exactly what it has always done, changing, restlessly and unpredictably, in ways that scientists are only now able to observe with real precision. The pole will keep moving, quietly, towards Siberia, or wherever the balance of forces deep in the core takes it next. The weak patch over the South Atlantic will keep evolving, its 2 lobes drifting and strengthening and fading, according to a process still being deciphered, field season by field season. Somewhere, in an unglamorous, magnet-free observatory building, a needle will keep tracing its daily rhythm onto a chart, the way it has for 150 years. Somewhere over the ocean, a survey vessel will keep towing a magnetometer behind it, patiently mapping stripes of ancient rock. Somewhere in orbit, 3 small satellites, older now than anyone expected them to remain useful, will keep circling the planet in careful formation, listening for the faint, ever-shifting signal rising up from 3,000 kilometers below. And somewhere, eventually, a piece of this puzzle now considered an open question: why the pole sprinted and then slowed? Why one side of an ocean anomaly weakens faster than the other? What exactly is happening to the shape of the world's innermost sphere of iron? Will finally click into place, the way Gauss's equations once did, the way the striped rock of the seafloor once did, the way a lodestone spoon balanced on a bronze plate once quietly hinted, centuries before anyone understood why, that this ordinary-looking planet was, from the very center of its iron heart outward, gently and continuously magnetic.